Greetings of the day, dear students. Today in this video, we are going to discuss one important topic, equivalent circuit of transformer. With respect to this topic, most of the students are feeling difficulty while attempting the question on this topic. In this video, we will discuss in a detailed step-by-step manner how to draw the equivalent circuit of a transformer, right? And its main important terminology, all the terminology, circuit diagram, voltage, current directions, right, induced EMF, number of turns, all this important terminology, and how to draw its vector diagram, this phasor diagram, how to draw for this equivalent circuit, and also we will represent how to find out the impedances, resistance and reactance with respect to the primary or secondary. And finally we will discuss the summary, and also we will do one example where we will understand all its basics. Dear students, the difficulty the students are facing is mainly due to lack of not understanding the terminology. Lot of terminology will be there. You no need to get confused. Once you get command on this terminology, different variables and its names, then this topic will be very easy for you. If you understand its meanings, right? This topic will be very easy, and the final answers also will be, calculations are also very easy and simple, right? Yeah. Now observe, in order to simplify the problems or calculations part, right, we will transform the given entire circuit into either primary side or secondary side. If you recollect, with respect to the ideal transformer, so far we are saying the resistance and reactances are negligible, right? But with respect to the practical transformer, the windings will have their own resistances and reactances. In this diagram, this V1 represents the primary side voltage. Every terminology, two times you are going to get. One is with respect to the primary and another one is with respect to the secondary, right? So V1 indicates primary side voltage. This is the first point. And V2 indicates secondary side voltage. Similarly, I1 indicates primary side current, and I2, here observe, I2 indicates secondary side current. With respect to these four terminology, you won't feel any difficulty. Most of the students are writing these four: V1, I1, V2, I2, right? Now the primary side winding resistance is denoted with letter R1. R1 indicates primary side winding resistance. Similarly, primary side winding reactance is denoted with letter X1. Clear? And this overall, both together, resistance plus reactance. Okay, this impedance Z1 indicates the impedance on primary side. Coming to the secondary side, also we will have the resistance, secondary winding resistance R2, and secondary side reactance X2, and secondary side impedance Z2. Secondary side impedance Z2. So with this, major terminology is completed. And also one more important, even EMF induced in the primary side and E2 EMF induced in the secondary side. I repeat again, E1 is the induced EMF in the primary side, E2 induced EMF in secondary side. N1 indicates number of turns in primary side, N2 indicates number of turns in secondary side. N1 number of turns primary side, N2 secondary side number of turns. Phi, flux phi, linking both the coils, both the primary and secondary winding. So far clear? Good. Now instead of drawing like this, this indicates the equivalent circuit of the transformer. If you observe, this load ZL indicates the load impedance, and V2 voltage across the secondary side, and E1 induced EMF primary side, E2 induced EMF secondary side, N1, N2 number of turns. And now the important point is, whatever the current that is drawn by this primary side I1 is it is the sum of two components. It is going to supply I0 and I2 dash. This is very, very important, dear students. I2 dash and I0. So I0 indicates the no load component. I0 indicates what? I0 indicates no load current. No load current. I2 dash indicate the load component of primary current. Now one more important point, dear students. This I0 no load current again will be divided into two parts or resolved into two components. What are those? One is the working component IW and another one is the magnetizing component IM. Just if you have already watched the ideal transformer concept, there we have already discussed how to resolve that I0 into two components. One is the horizontal component and another one is the vertical component, right? So now this I0 is resolved into working component and magnetizing component. This I2 as usual, this I2, this current in the secondary side flows through the R2 and X2 and it flows through the load. So these are all the important terminology. If you once understand these terminology and the name of the variable, then this topic will be very easy, right? Yeah. Now we will see the phasor diagram. Observe, dear students, whatever voltage, the input voltage you have applied, some part of voltage is wasted or dropped across R1 and X1. There will be some drop of the voltage, of the applied voltage, there is some drop across R1 and X1 because current is flowing through that winding also. Now that remaining part only will be available as induced EMF E1. If you understand this point, then equations will be very easy for you. What I want to say is, don't think that whatever the applied voltage V1 will be available as E1, induced EMF. During ideal transformer case, we have told like that. Whatever V1 that is available as E1, but both will be out of phase by 180 degrees. That is what we told you in the ideal transformer concept. But practically there will be some drop in the voltage. Because of that drop, out of total applied voltage V1 minus drop will be E1. Very, very important. Now if you observe E2, with respect to the E2, whatever voltage is induced in the secondary is equal to, there is some drop here, plus remaining will be only available across load. Very simple, dear students. It is something like this. For example, if V1 equal to 100 volts, if there is some 10 volts drop, then your E1 will be how much? Just for understanding sake I am telling. Applied voltage V1 minus drop 10 volts. 100 minus 10 will be available. Now induced EMF E2, for example, E2 equal to some 80 volts and there is some drop of some 8 volts. Now what will be available across load? This induced EMF 80 minus 8, around 72 volts will be available across, load. Like that you have to understand. Clear? Just for understanding sake I have taken these numericals, but now let me see. Now I1 and V1, the current flowing in the primary and the voltage applied V1, there will be some angle between those two. That angle is phi. That angle is how much? Phi. Right? So this is what we have written here. This equation is very, very important. Just now I have told. V1 is equal to V1 equal to I1 plus E1 plus drop at both resistor and reactance I1 plus Z1 I1 Z1. V1 equal to E1 plus I1 Z1. Similarly, the voltage V2, voltage across load, will be equal to induced EMF secondary side minus drop E2 minus I2 Z2. These two equations are very, very important. Clear? Okay. Now, what is the impedance? Impedance on the primary side, Z1 root over R1 square plus X1 square, because primary side you are having a resistance like this and reactance like this. If you have you have seen in the DC circuits and AC circuits chapters, the impedance is given by Z equal to R1 plus J X1. If you want mod Z is given by root over R1 square plus X1 square. That is what we have written here. Root over R1 square plus X1 square. And similarly impedance Z2, secondary side impedance Z2 equal to root over R2 square plus X2 square. Clear? Yeah. Next. So this diagram, one thing is very clear for you. V1 equal to E1 plus I1 Z1. That is just simply we will add here. You will have V1. You are having V1. And the angle between this V1 and I1. V1 and I1. There is some angle difference. First you draw these two. Phi 1. Clear? Now on x-axis we will have flux. This is standard. On x-axis we are going to have the flux phi, and some small amount of current I0 will be drawn. I0, no node current I0 is drawn. Now this for this voltage you have drawn already the voltage, right? And EMF E1 is given by V1 minus I1 Z1 is equal to E1, or in another manner this is also same as V1 equal to I1 Z1 plus E, I1 Z1 plus E1. So you just, this is the drop I1 R1, and for drop across resistor, this reactive drop, voltage drop due to the reactance will be exactly 90 degrees with respect to the I1 R1. Now the sum of these two, I1 R1 plus I1 X1, will be our impedance I1 Z1. This is what we have drawn here. I1 Z1, I1 R1 plus I1 X1 is our I1 Z1. Now if you observe this E1, this is minus E1. Now its opposite direction will be plus E1. Understand? Like this you have drawn minus E1. The representation is given as minus E1. Then what will be the E1? E1 will be quite opposite. E1 will be the quite opposite to that one, right? Now this V1 minus I1 Z1 equal to E1. V1 minus I1 Z1 equal to E1. That is what we are getting here. This is V1. So here I1 Z1 arrow direction, observe. Dear students, observe the direction of I1 and Z1. It is upwards. So its opposite direction will be minus I1 Z1. Minus its opposite direction will be minus I1 Z1, right? So V1 minus I1 Z1 equal to minus E1. If you add this V1 minus I1 Z1, we will get this E1. We will get this minus E1. Right. Similarly for secondary side also. Secondary side also what happens is, secondary side some voltage V2 you are having, and a resistive drop will be in phase. Some I2 R2 drop, you are having some current like this, and there is some resistive drop. For resistive drop exactly 90 degrees, there will be the reactive drop. This is exactly 90 degrees. You will have I2 X2. You are having I2 and X2. If you add those two, I2 R2 and plus I2 X2, we will get the impedance I2 Z2. I2 Z2. Now this V2 plus I2 Z2 will be our E2. This is our E2. Very simple. Everything comes from these two equations only. If these two equations are familiar, then easily you can draw this diagram. Clear? Yeah. So this is the if it is the resistive load. If it is a resistive load and uh, on the transformer, this will be the vector diagram, right? If it is some other load, there will be some voltage, there will be some angle difference between the voltage and current. There will be some angle existing. Here in this context, both V2 and I2 are in phase. They are drawn on the same line. If this is some V2 and I2 is also drawn on the same, because resistive load V2 and I2 will be in phase. There won't be any angle. If it is some other load, here we have drawn V2 no. For this V2, if it is inductive load, I2 lags V2 by some angle. If it is rarely you won't have capacitive load, most of the times either resistive or highly inductive loads we are going to have, right? Yeah. Now resistance and reactances will be transferred from one winding to the another winding, right? Why we will do this is because the calculations part can be made simple. All the calculations we can do with respect to either primary side or secondary side. So how do you understand that? For example, if there is a resistance R2 in a secondary, that value will be same as R2 by K square if it is transferred to the primary. If it is transferred to the primary side. How it is derived means, even though it is on primary side or secondary side, the losses must be same. Losses must be same. So if it is in the secondary side, what is the loss? What will be the amount of loss? I square R, because current flowing is I2 square and the resistance is R2. It is something, for example, you are having a transformer like this and you are having only primary side resistance, and secondary side resistance you are having R2. Now what will happen? The same R2 will be shifted to the primary side. Then that value should become how much? R2 by K square. If you bring this resistor to the primary side, then it is to be denoted with letter R2 dash. Then you will draw like this. This R1 will be same, but this resistor part you will remove from the secondary side and you will place it in the primary side. But now the name is to be given as R2 dash. Very, very important. The name or variable name. Now there won't be any resistor in the primary side. Now while while transferring this resistor from secondary to primary, its value must be, it does not mean that, for example, here it is 100 ohms. If you transfer it to the primary side, then also the value will be 100 ohms. No, you don't understand like that. That value must be equal to, R2 dash must be equal to its previous value, R2 divided by K square. That much value you have to place in the primary side if you are bringing the secondary side resistor towards the primary side. Very, very important. The name you should give is R2 dash. it is to be understood as secondary resistance referred to primary R2 dash. In all the textbooks, everybody will follow the same notation. Now R2 dash means the secondary side resistance referred to primary. Right? Now, as we told you that the copper losses in secondary is how much? I2 square R2. Now this loss is to be supplied by the primary current, but what is the current flowing in the primary? I1. Now with respect to the new shifted value, this I1 square R2 dash must be equal to I2 square R2. This is very important for entire derivation. In this entire equivalent circuit concept, this is the major key point. Losses. Even though you transfer from secondary to primary side or primary to secondary side, the losses must be same. Based on that point, we will get this derivation. Now, I1 square R2 dash must be equal to, before transferring, what is the loss in the secondary side? Secondary side current is I2. Secondary side resistor value is R2. So, I2 square R2. So this is the loss before transferring and this is the loss after transferring towards the primary. If these two are equal, then the equivalent circuit transformation is completed. Based on that condition, now what will be your I2 R2 dash? R2 dash equal to I2 by I1 whole square into R2. But already we are familiar, I2 by I1 equal to how much? 1 by K. I2 by I1 equal to how much? 1 by K. Therefore, our R2 dash is equal to R2 by K square. R2 dash is equal to R2 by K square. Very simple, dear students. For example, before transferring, if you take K equal to 2. Before transferring secondary side, it is 100 ohms. Now if you bring it towards the primary side, that value must be equal to how much? 100 divided by K value is given 2, 4, 25 ohms. Whatever that is there as 100 ohm in secondary now will become 25 ohms in the primary. Very simple. Similarly, if you shift this R1, for example, if you are having some 50 ohms, if you want to shift it towards the secondary, if the K value is 2, how much it will become, do you know? For example, it is removed from the primary side. Now you are shifting it, you want to shift it to the secondary side. Secondary side already R2 is there. It won't get disturbed. R2 is fixed. How much? 100 ohms. Now you are shifting the resistor in the primary side to secondary side. What is the name you should give? R1 dash. Very important. The name you should give is R1 dash. Now what will be your new value? K square times R1. What is K? In this example 2. 2 square into, before shifting, what is the value? 50. For example, so 4 into 50. Now it becomes 200 ohms. The same 50 ohms now became how much? 200 ohms in secondary side representation. Like that you have to understand. If it is primary, this 100 ohms became how much? 25 ohms. Now this 50 ohms became how much? 200 ohms. Very clear? So R1 dash equal to K square times R1. If you are feeling difficulty for understanding, you just simply take some numericals, then you will get very much clear cut idea. This is some 50 ohms, 100 ohms. Before transferring, I want to transfer R2 to primary. It is simply R2 divided by K square. If K, you take assume some value, K equal to some 2, it becomes 25 ohms. Similarly, you want to shift primary to secondary. Before shifting it is 50 ohms. Now you are shifting. Its new value must be R1 dash equal to K square R1. K is given 2. You know the old value. Now the new value will be 200 ohms. Right? Yeah. So now the same concept applies for all resistances and reactances. Now we have drawn that entire thing in the form of a diagrams here. Dear students, now observe, you have removed secondary side resistor and you have brought it to the primary side, and you gave the variable name R2 dash, very important. Secondary resistor referred to primary. Now this R1 and R2 dash, you should give one more name. That is called R01, very important, R01. Don't get confused. Previously R2 is there in the secondary, you brought it towards the primary side. The name you given is R2 dash. Now primary side already R1 is existing. Now this R1 plus R2 dash is to be called as R01. Now that is what you have written here. This is to be read as effective resistance. Effective resistance of transformer referred to primary. Sorry. Effective resistance of transformer referred to primary R01 equal to R1 plus R2 by K square. Similarly, you can remove the primary side resistor and shift it towards the secondary side. You gave the name as R1 dash. Primary side resistance referred to secondary. Its meaning is, now this R2 plus R1 dash is called R02. R02. Its name is, it is to be read as equivalent or effective resistance of transformer referred to secondary. Equivalent or effective resistance of transformer referred to secondary. Clear? Yeah. Now it is equal to R2 plus R1 dash. Just now you have seen R1 dash equal to how much? R1 into K square. Clear? Good. The same analysis is applicable for reactance also. Now what about reactance? How do you understand this X2 dash? You have brought the secondary side reactance towards the primary. Now X01, effective or equivalent reactance of transformer referred to, one is there, primary, referred to primary. X01 equal to X1 plus X2 dash. But what about X2 dash? X2 by K square. Similarly, entire reactance is brought towards the secondary side. So X02 equal to X2 plus X1 dash. X2 plus X1 dash. But what about X1 dash? K square times X1. Whether it is now you have found out the resistance and reactance. Together we will call it as impedance. We will call it as impedance. Now Z01, impedance, equivalent impedance referred to primary, Z01 is simply R01 plus JX01. For example, already in DC circuits and AC circuits you are familiar. If R and if you are having some R plus some JXL, R and inductive reactance is there. What about its impedance? It will have some real part plus imaginary part. R plus JXL. If it is inductive reactance or capacitive reactance, based on that plus J or minus J you will get. If it is inductive reactance, plus J you will get. If it is capacitive reactance, you will get minus J. Clear? Yeah. Now, as it is winding, inductive in nature, we will get plus sign here in this context. Right? Yeah. Now, Z01 equal to R01 plus JX01. What about its mod Z? Root over R01 square plus X01 square. This is Z01. Similarly, secondary side. root over R02 square plus X02 square. So this is all about the transferring the resistance, reactance and impedances from one side to another. In this entire concept, the whole terminology, if you are familiar with the terminology, you won't feel it as a difficult, right? Now, finally the impedance is also transferred. These are the diagrams, equivalent R01 plus X01. If you observe, this R02 means nothing but R2 secondary side resistance plus primary side transferred to secondary R1 dash. Together we are calling it as R02. R02 plus X02 we are calling it as Z02. Very simple. So this entire half an hour discussion is brought in a simple summary like this for these three. If you remember this concept is completed. This entire half an hour discussion is for at last for these formulas. R01 equivalent resistance referred to primary. It is having R1 plus R2 dash. R1 plus nothing but R2 by K square. R02 R2 plus R1 dash. Nothing but R2 plus R1 into K square. Clear? Now we will see one example problem so that you will understand. So on observing this problem, dear students, please focus. 100 kVA 440 by 4400 by 4400 by 220 volt single phase 50H transformer has R1 R1 equal to 2.45 ohms, R2 equal to 0.008 ohm, and the value of reactances are X1 equal to 4.2 ohm, X2 equal to 0.015 ohm. Calculate for the transformer equivalent resistance as referred to primary, equivalent resistance as referred to secondary, equivalent reactance referred to both primary and secondary, equivalent impedance referred to both primary and secondary, and also total copper loss. Total copper loss. Dear students, first write down the data given. Whatever the data is given, if we know the terminology, then easily we can write its variable names. Variable names. Observe, the power is given 100 kVA, 100 kVA, but we know the formula for that power V1 I1, that is simply equal to primary side V1 I1 equal to 100 into kilo is given. So 100 into 10 power 3. Next one. Somewhere if you see some representation like this 440 by 220, its meaning is primary voltage V1 equal to 4400 volt and secondary voltage V2 equal to 220 volt. Secondary voltage V2 equal to 220 volt. Primary winding resistance R1 is given. We should understand. Simply he gave you only R1. Then we should understood it as it's a primary winding resistance because 1 is there. The subscript 1 is given. So primary winding resistance R1 equal to 2.45, R2 secondary winding resistance 0.008, reactance X1 is there. Based upon this subscript 1, we can write it as primary reactance X1, X2 is there, secondary reactance, right? So with this data given is completed. Now first thing we have to find out is the value of K, right? What about K? V2 by V1. V2 is already given 220 divided by V1 4400. The value of K is 0.05. Clear? Now how much current will be drawn? You already know the formula for power. V1 I1 is known. If you simply divide this power with V1, right, we will get the value of current. V1 I1 is 100 into 10 power 3 divided by V1. V1 is 4400. Now this is the value of current. I1 is we got I1 22.72 amperes. Similarly I2, if we want I2, the same power will be available across the load. V2 I2 divided by V2. If you take, we will get I2 value. So I2 equal to same power divided by, now the voltage is V2. So this is the secondary current, 454.54 amps. So now we got the currents. The first question, equivalent resistance referred to primary. We know the notation, R01 equal to R1 plus R2 by K square. You already know R1 2.45 plus R2 0.008 divided by K square 0.05 whole square. Its value is 5.65 you will get. In this entire discussion, the key point is, if you don't know this formula, we cannot go further. R01 equal to R1 plus R2 by K square. That is why I have written the formulas in the summary. In order to do the problems, if these 6 formulas are known, last 2 are easy. First 2 if you remember, the same thing will be applicable for the reactance also. So dear students, please don't neglect to memorize this R01 formula and R02. Clear? Yeah. Please practice that formula. Now R02, resistance, equivalent resistance referred to secondary. Simply R2 plus R1 into K square. R1 into K square. We will get it as 0.0141. Now for reactance, X01 equal to X1 plus X2 by K square, 10.2 ohms. X02 0.0255. These 4 formulas. Then only we can able to solve the problems. If we don't memorize these formulas, it will be difficult. Now impedance, Z01 equal to root over R01 square plus X01. Just now we have calculated R01 and X01. Observe, R01 is how much? 5.65. X01 is how much? 10.2. R02 0.0141. X02 0.0255. So those things we have to consider for impedance. That is what we have done here, root over R square plus X square, 11.66. Similarly for impedance Z0. So what does it mean? Now the power loss I square R. In any circuit, if somebody asks you if some current I is flowing, if R is the resistor, power P equals to VI. In the place of I, from Ohm's law, V equal to IR. In the place of I, you can write V by R. So V equal to IR. So P equal to IR into R is nothing but I square R, power loss, I square R. How much is the power loss? I square R. Now in this context, primary side current is I1 square, primary side resistance is R1 plus secondary side current I2 square plus into resistance R2. That is what we have done here. So these are the amount of loss, 2171.5 watt. So this is the copper loss. So this is what the equivalent circuit looks like. So R01 is how much? 5.65. R02, these values. Now this entire values we have transferred to the primary side with simple R01 and X01. R01 and X01. So this is what all about the equivalent circuit of a representation of a single phase transformer. Clear? So dear students, please watch this video once again if required, right? And this concept is important. There are chances for problems also to be asked on this topic, right? Please don't neglect this topic. This is an important topic. Just simply practice. Terminology is important in this entire topic. Terminology is important. You please write down all those points at one place in a notes, then it will make easy for you. Okay.